Session 12. Session 12 is settling. So the settling types. The first is discrete particle sedimentation, type 1 or free settling. We have two laws. The first law is Newton's law. 1.1 is Newton's law. If you have a particle, as you see here, the particle, we will have force buoyancy, force drag. So FB is impelling force or force buoyancy, and the resultant will be velocity of the settling based on these forces. So forces based on the Newton's law from the dynamics, if you remember, sigma forces equals to mass times acceleration. So Newton's law, V is settling velocity of particles meters per second. The formula is Vs equals to root of 4 times gravity over 3 times CD times rho s minus rho over rho times d. So this formula we need to use for Reynolds number larger than 1. So from fluid class we know that Reynolds numbers are above 1. We classify the fluids as transition or transitional fluid and turbulent fluid. So rho s in this formula is a specific mass density of particle in kilograms per meters cubed. Rho is a specific mass density of the liquid in kilograms per meters cubed. G is acceleration of gravity, 9.81 meters per second squared. Again, this is for Reynolds number of larger than 1, so that is Newton's law. And CD is coefficient of drag, which is function of Reynolds number. So we have to define what is Reynolds number. We did so in fluid mechanics. Again, we'll go and see how we can classify CD. Again, for Reynolds number less than 1, we classify fluid as laminar fluid. Reynolds number will be 24 over Reynolds number. So CD for Reynolds number between 1 and 10,000, which we classify these fluids as transitional fluid, will be 24 over Reynolds number plus 3 times 3 over root of Reynolds number plus 20 plus 0.24. And for turbulent flow, which Reynolds number is above 10,000, the CD or drag coefficient will be 0.4. And the Reynolds number RE for the sphere is defined as so drag coefficient for spheres, disks, and cylinders. As you see here, we have a graph that is Reynolds number dv rho over mu. That is how we can find Reynolds number. D is diameter, V is velocity, rho is density, mu is viscosity. And you can find all of these parameters in your F. Emanuel property of water. And then in y-axis, that is drag coefficient, CD, and in the x-axis, this is dv rho over mu, that's Reynolds number. You can find for cylinders, for disks, and spheres. So for spheres, disks, and cylinders, you can find a drag coefficient. So again, Reynolds number versus CD. Stokes law is Vs equals to G times rho P minus rho dP squared over 18 mu. Stokes law, that is for laminar flow. From fluid class, we know that Reynolds less than 1 is, we classify the fluid as laminar flow. Denser and larger particles have a higher settling velocity. So CD will be 24 over Reynolds number. 24 times nu over Vs times d. So nu is viscosity, V is velocity of settling, d is diameter, and Vs you can find from this formula. So G rho is G or specific gravity minus 1 over 18 mu times d particle squared. Here's an example. Example 3. Determine the distance a particle will settle in an hour if the particle has a specific gravity of 1.01 and the diameter of the particle is 0.5 millimeter. Assume the water temperature is 15 degrees of Celsius and Reynolds number is less than 1. So A is 0.11, B 1.1, C 0.43, and D 4.3. So please pause the video here and try to solve it and then play for the next slide to see what is the answer. Okay, Vs equals to 0, a specific gravity minus 1, diameter of particle squared over 18 times mu. In old version, FE page 110, that is the property of the water. Maybe your FE manual, if you use the new version, should be 112. So let's see it. For temperature of 15 degrees Celsius, rho is 999.1 kilogram per meters cube, and mu from the same table will be 0.001139. Specific gravity is given 1.01. Diameter of particle is 0.005 meter. So let's plug numbers in. 9.81 times 999.1 times, there's typo here, and then 1.01 minus 1 times 0.005, so 0.0005 squared over 18 times 0.001139. If you plug the numbers in, so take your time and pause the video here and try to find the answer. If you find the answer will be 0.0012 meters per second. And then here, now you have velocity, how we can find distance. Again, pause your video here and think how we can, based on the velocity, how we can find distance. If you remember dynamics class, distance equals to velocity of settling times time. So velocity we found here is 0.0012 meters per second times 1 hour. Detention time is 1 hour. In 1 hour it will be 3600 seconds. And again, one more time, pause the video here and see what is the answer. So if you find the answer will be 4.32 meters. So the answer A, B, C, D, the answer will be D. So discovering the horizontal velocity in sedimentation basins must be controlled to a value less than what would carry the particles interaction along the bottom. Means that is discovering. Means discovering the water will wash out the particles. You have to design to maximum velocity. So V will be horizontal velocity in meters per second. The formula is V equals the root of A times beta S minus 1 GD over F. So beta is constant for type of discovered particles. And S will be a specific gravity of the particles. G will be gravity, 9.81 meters per second. D is diameter of particle, and F is Darcy-Weiss friction factor, 0.02 to 0.003. This is the range for friction factor. Settling basin. Settling basin. So we designed to minimize turbulence. As you see here, this is a tank, and there's inlet, there's outlet, and this is the depths of the water. So we have to define some parameters. The first parameter we define is overflow rates. Overflow rates are used for design. So V initial is overflow rate. So will be flow rate in, or Q in meters cubed per second per settling surface area. So the flow that you have Q over area. What's the area? Area will be top area. Means the length, as you see here, length times width, that will be the area. Q over area will be overflow rate. So let's see what will be the unit. Meters cubed per second over meters squared. You can cancel out meters squared here. The left over will be meters per second. Meter per second, and that is unit for velocity. The question is the velocity of the water in what direction? In vertical direction or horizontal direction? If you divide Q over this area, the velocity will be in vertical direction, means how fast particles are settling down in the tank. Settling basin design. This is typical design. This is typical criteria for settling basin. So basin floor area will be 41 liters per minute per meter square of flow, 250 to 410 liters per minute per meter width of the weir for outflow. Submerged inlet weir will be 15% of basin water depth. We use 25 centimeter wide weirs and we use rounded edges and maximize length of settling chamber as much as possible and as much as you can. So from previous class, we know that the first unit will be rapid mix. After rapid mix, water goes to flocculation tanks. Here you see flocculators. This is rapid mix. And then you have flocculators here. After flocculators, water enters to a sedimentation tank. After particles settle down at the right end of the sedimentation tank, at the top end, you collect the clean water or purified water. And here you see that here, this is one full and one empty settling basin or settling tank. Settling tanks, basins, or clarifiers. So there's two types. One is rectangular and another one is circular. Rectangular basins or clarifiers are basins that are rectangular in plans and cross sections. In plan, the length may vary from 2 to 4 times the width. The length may also vary from 10 to 20 times the depth. The depth of the basin may be vary from 2 to 6 meters. We do not go more than 6 meters, as we talked before. That is because of construction costs. The influent is introduced at one end and allowed to flow over the length of the clarifier toward to the end or toward to the other end. So here, circular basin, as you see in the picture, this is the top view or this is a plan and this is profile. So rectangular basin, this is plan as you see here, top view or plan, and this is cross-section view. Here another basin, this is water enters here, and there is one baffle. So we put baffle, and after baffle, perforated baffle. We want to equally distribute water all over the settling tank, and here is settling zone, and at the end there is effluent weir to collect the. So let's see, assume that we have here one settling tank. Let's see what will happen to the one particle. If this one is at the left edge, if this is a particle, if I play, I will see that the particle will settle down at the right edge. So if we consider height as h and the length as l, so we have two different velocities. The first velocity, horizontal velocity, or v1. So v1 is horizontal velocity of liquid flow. And the second, as the yellow one, as you see here, that will be vs. That will be settling velocity of particle. So the first one, v1, horizontal velocity, and the second one is settling velocity of the particle. So a particle that is just removed has a settling velocity, which is v initial. So v initial will be height over time, or q over area. So where time will be v over q. So A is the surface area of the basin. So V is the volume of the tank, Q is flow rate in meters cubed per second or feet cubed per second. V can be in meters cubed or feet cubed. Critical settling velocity and overflow rate. So if you consider the water, let's say here is 50% up, 50% bottom, and if you have flow here, and if at the half will be half velocity, and at the top will be half velocity. If from the edge to edge will be full velocity, it means that one particle finally should settle down at the corner or should be captured at the end. Otherwise, that particle will escape from the tank. So we have velocity, which is V initial. So V initial expressed in units of velocity, feet per second or meters per second, which is the critical settling velocity. Critical settling velocity is the settling velocity of particles which are 100% removed in the basin. V initial expressed in units of flow per unit area, which is called overflow rate, and we defined this before in previous slides as well. As you can see, the only difference between critical settling velocity and overflow rate is the type of unit used to express the number. The critical settling velocity and overflow rates are the same number, but proper units should be used to express each. Since smaller particles have lower settling velocities, if you want to remove smaller particles in the settling basin, you have to have a lower overflow rate. Since V initial equals to flow rate over area, to have a smaller V initial, you have to have a large area. A bigger basin removes smaller particles. So let's see what is the typical dimensions of sedimentation tanks. For rectangular tanks, dimensions, the range for depths is from 3 to 5 and typical is 3.5 meters. For the length, it can be from 15 to 90 meters and typical numbers are from 25 to 40 meters. The width in meters is from 3 to 24 and typical number 6 to 10. That is for rectangular. For circular, the diameter can be from 4 up to 60 meters. Typical numbers we design from 12 to 45 meters. The depths from 3 to 5 or typical number 4.5. We talked about this one before. We do not go over 5 meters because of construction cost. Bottom slope in millimeters per meter, it can be from 60 to 160 or typical number will be 80. Example 2, the water treatment plant has a flow rate of 0.6 meters cubed per second. The settling basin at the plant has an effective settling volume that is 20 meters long, 3 meters tall, and 6 meters wide. Will particles that have a settling velocity of 0.004 meters per second be completely removed? That's the first question. If not, what percent of particles will be removed? Please pause the video and try to solve this problem. So the answer, we know that the V initial will be Q over area, that will be 0.6 meters per second, over, that is Q, 0.6 meters cubed per second. Here there's typos, it should be 0.6 meters cubed per second over area, or area will be 20 meters times 6 meters. The answer will be 0.005 meters per second. Since V initial is greater than settling velocity of the particle of interest, they will not be completely removed. So what percent? The percent of particles which will be removed may be found using the following formula. The percent removed will be Vp or V initial times 100. So here will be 0.0004 divided by 0.0005, that you find it. And here 0.004, the particles are given, times 100, that will be 80%. Example 3, how big would the basin need to be to remove 100% of the particles that have a settling velocity of 0.004 meters per second? So please take your time to answer the question. Solution. So velocity initial or flow rate should be equal to Q over area. Q is flow rate and area is the top view area. So we know that the velocity here is given, should be 0.004 equals to the flow rate is 0.6 over area. So take your time and put the data, and if you plug the numbers in, the area will be 150 meters cubed. Now you know the area and you know the width, and if the basin keeps the same width, you are looking for the length. And we know that the area, which is 150 meters cubed, should be equals to width times length. Width is 6 meters times length, and from here length you can find the length as 25 meters. So next question, determine the terminal settling velocity for a sand particle with an average diameter of 0.5 millimeters and the density of 2600 kilogram per meters cubed settling in water at 20 degrees of Celsius. Density and viscosity values may be found in your book, or you can find in the table, which is the property of the water in fluid mechanics section. First, you need to put a formula. The formula is gravity times rho particle minus rho water times diameter of the particle squared over 18 times mu. Gravity. First, because here, as you see here, you don't know that's laminar flow or that's turbulent flow. So first you will use the Stokes law to see what is the velocity settling. So gravity is 9.81 times 2600 is given here minus 998.2, that is a rho of the water in 20 degrees of Celsius, times 5 times 10 to negative 4 meter. So that is the diameter, which is 0.5 millimeters, squared over 18 times mu. So if you go to the table, it will be 1.002 times 10 to negative third. So from here, you will find 0.22 meters per second, 0.22 meters per second. Now you have velocity, you have to check your Reynolds number. So the Reynolds number, if you compare this formula, 5 times velocity S times dP times rho water over mu. Please compare this one with your FE manual. You can search Reynolds number in the soft copy of your FE manual, or hard copy in fluid mechanics section. You see that there is another parameter here, that's phi. Phi is the shape factor. So let's say that shape factor for the sand that you consider here is 0.85. So 0.85 velocity you found from previous slide, that's 0.22. Diameter of the particle is 5 times 10 to negative 4, and the rho is 998.2 kilograms per meters cubed, and mu will be 1.002 times 10 to negative third. So from here you find Reynolds number 93. So Reynolds number is 93. So again, now because the Reynolds number that you calculated is greater than, so it is greater than 0.3, but you can consider 1. So you can use the other formula. First, you have to find direct coefficient. Direct coefficient is 24 over Reynolds number plus 3 over NR plus 0.34. If you remember, we had laminar flow, turbulent flow, and transitional flow. So here, Reynolds number that you find from previous slide, you will plug in this formula, and you will find CD as 0.91. And now part B, you will find velocity. As you see here, the second formula. Velocity try to find this one in your FE manual. Velocity settling in environmental section in water treatment. So over there, velocity settling will be root of this formula, or velocity settling squared equals to 4 over 3, 9.81 times particle, rho of a particle is 2600, the rho of the water is 998.2, times diameter is 5 times 10 to negative 4 divided by 0.91, that is the CD, times rho of the water is 998.2 kilograms per meters cube. If you calculate, velocity settling will be 0.11. If you compare with the previous slides, this problem is trial and error. You started with 0.22 and you calculated and you ended up with 0.11. So in your trial in decimals, you should have same number. 0.22 is not same as 0.11. So you have to go one more step. The next step, you will go to 0.11. Then the next step, one more time, you will put your Reynolds number. So 0.85 same, but this previous formula, just you will put 0.11. So and the other information is same. You will calculate Reynolds number 46.5. And then you will put 46 because this number is larger than 1 and less than 10,000. So you should use transitional flow. So we had three flows. The first one was laminar, the second was from 1 to 10,000, that is transitional from 10,000 and more, that will be a turbulent flow. So you will plug your number in here and you will find 1.3, that is CD. And then you will put in the velocity settling, so that this will be for Stokes law, and the same formula will forward 9.81, 2600 minus 99, 8.2 times, diameter is 5 times 10 to the negative 4 over 1.3, that is a Dirac coefficient, times 998.2. From here you will find velocity settling 0.09. So if you compare one more time, 0.09, the previous velocity was 0.11. Still in decimals are not same. One more step. So the second, repeating steps 2 and 3 using the data from step 4 yields number. So if you do, Reynolds number will be 38.1, Dirac coefficient will be 1.46, velocity of settling will be 0.085. Still, it is not same in decimal. Repeating steps 2 and 3 using the data from step 5 yields again. So Reynolds number will be 36, Dirac coefficient will be 1.51, and velocity of settling will be 0.083. So the above estimate of the velocity is sufficiently accurate. I mean, it's decimals, as you see, is 0.08, 0.08, and you will stop here. Flocculation particle sedimentation type 2. That was all of the calculations that we did before. It was just for one particle. Settling of flocculent particles in diluted suspension, that is type 2. Zone or hindered, so it will be type 3, and compression settling type 4. These are for wastewater. So these type of settlings happens when concentration of particles is high enough that fall velocities are affected by adjacent particles. The type 3 suspension then changes to a type 4 suspension characterized by shallower interface. This type of settling occurs mostly in chemical treatment plants and wastewater treatment plants in thickening zone. So we can say that these are for wastewater, that is for sludge blanket. One sludge blanket goes down and all of the particles and captures all of the particles, and all of the particles as a cloud sinks to the bottom of the tank. So again here, flocculation settling or type 2 settling particle trajectory, as you see here in parabola, and the particles settle down to the bottom of the tank. But how you do, you take to the, so we are not going to here to work on type 2, type 3, and type 4, but if you want to work, you take sample from wastewater and you take it to the lab, and the lab, you see here, there's a column, and from different altitude, different actually levels, you take samples, and after you take samples, so here you say that based on what is the settling time, for TSS and removal efficiency, you find what will be total efficiency of this treatment. This is one sample. Here you see another view for settling tank. In settling tank, you have influent and you have effluent, and you have here a sludge blanket, and there is a bridge here, and then this bridge, and so at the bottom, as you see, the bridge spins and collects all of the sludge that is sinks to the bottom, and the effluent that is cleaned wastewater you collect from the top. Again, this is another view. You see water enters as a queue at the left, and then you have settling zone and the sludge zone at the bottom. Again, another view. So A at the top, B, again, you see sludge zone at the bottom. So here, settling zone at the middle, that's an inlet zone. And you take water or waste cleaned or purified wastewater from the top as outlet zone. So another view here at the bottom, as you see, these are as you see here, the bridges you see here, that is for removing sludge. It spins and collects all of the sludge at the bottom. Here another view that is empty one, as you see at the bottom, that's collectors, and you see here and the circular tank. One more time, that is circular tank. Another view for the tank, that's for rectangle. As you here, the perforated wall and it enters, and then at the end you collect purified wastewater. Another view that is for plant view or from the top view, you see the settling tank, and here collectors that you collect all of the treated wastewater. But here again you see another picture for circular settling tank, and as you see, these are steel V notches. The water, as you see here, flows freely to the side, and you collect from the sides and V notch, and these are weighers that you need to design based this formula, the same for weighers that we did in class in fluid mechanics. Now one problem. Problem 9. Determine the length of rectangle clarifier for a flow of 3 million gallons per day if the design detention time is 2 hours. The tank has a depth of 8 foot and length over width ratio is 4:1. So here take your time and see how you can answer this question. So A, B, C, D, which one is the answer? So let's go. So the solution for the problem, time equals to volume over Q. If you have the tank like this, volume will be Q times time. So volume will be, Q is given 3 million gallons per day. 3 millions means 10 to 6 per day. 1 day is 24 hours. And time is 2 hours. From here you will find 25,000 gallons. Now you want to convert gallons to feet cubed. So it will be 25,000 times feet cubed over 7.48 gallons. From here will be 33422 feet squared. Now area equals to volume over depth. Our volume is the number that we found before over 8 feet. So if you find, the answer will be 4178 feet squared. Now you have the area, and we know that the area equals to length times width, but the length, so width is width, length, we substitute with 4 times width. Why? Because of the ratio that's given in the problem statement. Will be 4 times width squared, and that will be 4178 feet squared. So from here we find width is 32.3, and length will be 4 times width, that is 129.3 feet. So the answer will be A.